We would like, of course, to do better in terms of prediction accuracy. Unfortunately, there's quite a lot of variance in this data. So we've already been looking at intertweet time, meaning if there's a tweet T1 and T2, intertweet time is the number of seconds between them. But what we're trying to predict is more granular than this, right? Specifically, if it's been delta t seconds since the tweet occurred, we want to try to predict the amount of time, labeled p here, until the person tweets again. So in order to do this, we have to collect a bunch of training examples. So our training examples are going to look like this. We want lots of pairs of elapsed time since the last tweet and how far we have to go until the next tweet. To get an understanding of the variance in our data, let's create this training data from the given raw data and then make some graphs. You can see here we're just producing these very same points. From the given raw data in time until next, which is just the time between tweets, we produce a series of more granular points, how much time has elapsed and how much time to go until the next tweet. And we collect them together in the list data points. So to get an idea of variance, let's take a look at a few fixed points. Specifically, let's look at what the data looks like when 10 seconds has elapsed, 150 seconds has elapsed, and 100 seconds has elapsed. To get an initial idea about what the variance looks like in our data, let's fix it at a couple of points. Specifically, let's look at what the data looks like after 10 seconds has elapsed and 150 seconds has elapsed. Let's zero in on the 10-second graph first. So let's look at what this graph is saying. This is just a histogram saying that if 10 seconds has elapsed since my last tweet, how long did I have to wait until the next tweet occurred? So here, 0 seconds had to elapse until the next tweet occurred, and at the other end of the graph, 90,000 seconds has elapsed until the next tweet occurs. And as you can see, it's skewed strongly towards 0 seconds. Again, it looks like an exponential distribution. Now, let's look at what this looks like for 150 seconds. Again, this is a graph of after 150 seconds has elapsed since the last tweet, how long did we have to wait until the next tweet? At the left end, we had to wait 0 seconds. At the right end, 90,000 seconds. As you can see, again, looks just like an exponential distribution. In fact, let's look at a graph of the standard deviation. Again, the x-axis here is the number of seconds that has elapsed since the last tweet. So 0 seconds, 10 seconds, 20, and so on. The y-axis describes the number of seconds until the next tweet occurs. And this graph describes the standard deviation in that quantity. So as you can see, the spread of the times that we have to wait until the next tweet occurs increases as the time elapses since the last tweet. Let's visualize this another way. This graph shows a 95% confidence interval of the time we have to wait until the next tweet as a function of elapsed time. So after 20 seconds has elapsed, here's the spread of how long we have to wait. As you can see, it spreads all the way from 0 seconds to 30,000 seconds. After 60 seconds has elapsed, the spread goes all the way from 0 seconds to 35,000 seconds. So as you can see, this is just another way to describe the graph we just saw of the increasing standard deviation. The confidence band just increases as time goes on. This is just another way of saying that as time goes on, we're more and more uncertain of how long it's going to be until they tweet next. Any estimator that we create, which is a function of delta t, will do so by essentially averaging over this spread at any given point along the graph. Again, as you can see, the spread gets wider as the elapsed time goes on, reflecting greater and greater uncertainty in the data as the time since the last tweet grows. Elapsed time becomes less and less good at determining what the intertweet time is, and any predictor we make based on delta t will suffer from this. This problem is called inherent variance. Note, this is not the same thing as model variance, which refers to how the output of your model is sensitive to training data. Inherent variance refers to the following concept. Let's suppose that our real model, meaning the actual real-life phenomenon, was in fact a linear one, meaning you had some function f, and it was a function of the single variable x. As data scientists, we collect records of the form x, f. From these records, we will try to build an estimator, and we'll probably have a pretty easy time of it, right? For a given fixed value, x1, we will always see the very same value of f beside it, a times x1. Over and over, as we collect records, every time we see x1, we will always see a times x1 beside it. Now, let's suppose we introduce some noise into this situation. The way to think about this is, x occurs, but before we can measure it as f, some noise process occurs to x, and the result is the thing that we measure. The consequence is, now we no longer see the same f for a given x. The first time we see x1, we might see value 1 beside it. The next time, value 2, and so on. This spread of values, v1, v2, and so on, produces the confidence band effect that we saw earlier. That, of course, makes finding the right value to guess for a given x1 much more difficult. In the next video, we'll talk about sources of this variance and what we can do about it.